In the previous video, we have talked about the notion of norm-linear space, where we have a vector space that a norm has defined. So the concept of norm is to have some kind of mapping or a rule to determine the size of entities in a vector space. In this video, we are going to talk about inner product space. Now it's more like we have a product space between V and V, a product space of V with itself. And we're going to take a look at a member of each set, X and Y. These can be two different vectors. And somehow we're going to come up with a concept of a transformation or a mapping rule so that we can talk about something as the relationship between these two vectors. That relationship has a meaningful definition, meaningful concept in application. It could mean linear combination of x and y. It could mean co-occurrence of vector x and y, and other things. So let's dive into the definition of these mapping rule or the concept of inner product. Suppose we have the product space of V with itself and inner product, all right, that takes the two argument x from x and y, both from the same vector space. This inner product takes a value in real number. Okay. In order for this transformation to be a mapping that is called inner product, it satisfies one, two, three properties. The first property is that that mapping rule is symmetric in the argument. Inner product between x and y and x has to be equal. Secondly, this inner product has linear property in the first argument, which means if you scale the first argument by the factor of a, it's the same as the inner product between x and y with the scaling factor a. Inner product of x plus y with z, you can distribute it in the first argument. These two conditions can be wrapped up in a single condition. Is this? All right. And the third property is that an inner product of x with itself must be non-negative. That relationship concept that we talk about two vectors. If you take inner product with itself, it should return something positive. Um, and and if inner product with itself is zero, that's only occur when that vector itself is zero. So we have these three conditions in order for this mapping to be an inner product. The thing is, you have seen inner product in applications, like in everyday. First of all, this is inner product from undergrad level. In RN, one inner product you can find is that you take a linear combination x1 y1 plus x2 y2 and xn yn. You can see that it's very simple that symmetric property satisfy. This is equal to y comma x. You can see that all of the three properties here are satisfied, especially the last one. Inner product between x and x is actually x transpose x, and that is going to be the sum of xi squared. That is always non-negative. All right. And when this is zero, it only occur when x is zero. Okay. That's a very simple to see. This is called the a vanilla inner product because it's a definition uh, that you originally see in calculus and other classes in your undergrad level. How about I'm talking about a new definition of my new inner product. What if I have W that is positive definite matrix and I define a new inner product as Y transpose WX? For example, My W is 2, 1, 1, 1. You can verify that this metric is positive definite matrix. So instead of having my traditional inner product thing, now when I introduce this W, I can define on my own, right? I can say, oh, Y transpose WX is going to be is going to be 2x 2x1 y1, right? Plus 1 times x2 y2, right? Plus 1 x1 y2 plus 1 x2 y1. I hope you can expand this to here. Maybe. Okay. And you're gonna see that this is simply 2x1 y1 plus x2 y2 plus oh yeah, I don't have to repeat. It's just that you're gonna see like 4 linear combinations. All right. So you get different factors. The thing is, we can prove that this new definition that you just introduced is an inner product as long as W is positive definite matrix. First, let's verify symmetric property. Is this right? You use the second argument transpose and then WX. And how about YXW? So if you follow the definition, it's supposed to be X transpose WY. Okay. And because these two guys turn out to be scalar, you know that so if I transport the scalar, I should get the same variable, right? The same quantity. But after you transpose it, is Y transpose W transpose X. But my W is positive definite metric, so I can assume that it is symmetric, right? So as you can see, it has symmetric property. The linear property is very clear as well. Okay, if I take alpha x plus z with y by the definition that I just introduced, so it's second argument, right? Second argument w and the first argument alpha x plus z. Mhm. And you know that you can expand this product in this way. And then that alpha is just a constant. And now you can you can see that this is inner product between x and y and inner product between z and y. So you have linearity in the first argument. Last one, which is the non-obvious one, okay? The positive definiteness. If you take inner product with itself, by the definition, that's going to be the second argument, x transpose wx. And because W is positive definite matrix, you know this guy is always positive whenever X is non-zero. Okay. And because W is W is positive definite. So when this guy is zero, it only the case that X is zero. Because what you have assumed that is that Y is positive, not just positive semi-definite. Okay. You also see the use of inner product in the set of matrices as well. If I define, I also have, I also come up with this concept in mind that what if I wanna say something about a relationship or some closeness, some degree of mutuality between two entities in the state of matrices. So if I apply the concept of inner product and then I say, how about I use inner product of x and y as the trace of second argument transpose the first argument. You can also check with the same way that um maybe maybe I hope that it's not I hope that it's not hard for you to see that. Suppose x is m by n and y is also m by n, right? They because they both have to take from these the same product, the same vector space. So y transpose is going to be n by m, right? So y transpose x is going to be n by m, m by n, and the result is n by n. So the matrix you see here turns out to be square. And then you take the trace, which is the sum of the diagonal terms. Mhm. You can also would like to characterize in a more detailed way. So if x and y are matrices, how about I partition x into columns like this, and my y is going to be columns like this. So yk here that you see is not a scalar, but it's a column vector. So y transpose is going to be y1 transpose, y2 transpose, dot, 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 yn transpose. Remember here again, I use the concept of block matrices. When I transpose a block matrices, I just do it in a usual way, but do not forget to transpose everything inside. You transpose a row, you get a column, but don't forget to transpose everything inside. Okay. So in this form, y transpose x is going to be y1 transpose x1, y1 transpose x2, dot, 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 y1 transpose xn. And as you can see, you're going to get yk, xk in the diagonal. All right. And by this notation, what you actually do is that you take the sum along the diagonal. So it's going to be yk transpose yk, which is, all of these term is a scalar. Now I'm going to show that why this is an inner product. Can I just show only the symmetric? Maybe show all of them. What about the first one? The first one, the symmetric property, it would be trace of whatever you have here. It seems like you, by the definition, you take the second argument transpose x, right? So y inner product with x is going to be trace of x transpose y. Mhm. But because of the trace property, this one is a square matrix. The trace of a matrix equal to the trace of that matrix transpose. So you see that it's the trace of y transpose x and is equal to inner product with x and y. All right. The linear property is not hard it's not hard. Alpha x plus z y is the trace of, by the definition, is the trace of y transpose alpha x plus z. And as you see that you can expand everything inside, you can distribute it, all right? And then it comes to the fact that how about the trace of the sum of a matrix? You have two matrices, you sum it before, and then if you sum it before, and then you take the trace, is it the same as you take the trace of each one and then make a sum of trace? It turns out that the trace operator is obviously linear. So this is trace lambda alpha of trace y transpose x plus trace of y transpose z. And that is alpha xy plus zy. So this notion, this division, turns out to satisfy the second property of inner product. Last one, positive definiteness. How about you take an inner product with itself? You're going to have trace x transpose x. Is it non-negative? How would you conclude that? This is a gram matrix, all right? The gram matrix is always non-negative. So the eigenvalue of x transpose x is always non-negative. The trace of a matrix B is the sum of all eigenvalues of B. So the trace of X transpose X is obviously non-negative because all the eigenvalues of X transpose X is non-negative. How about whenever X transpose X is 0? Hmm. So as our calculation before, X transpose X is going to be x1 transpose x1 dot 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 xn transpose xn, right? And this is x xi transpose xj, right? In off diagonal term. So if the trace of X transpose X is 0, that's only occur when the sum square of xk square is 0. So that only happens when the matrix X, no, not square, sorry. Yeah, this is not square. This is not x square. This is norm of the column vector x square. Mhm. So that happens when the column of x is 0 for all k, and that's the same as the matrix X is 0. Okay. Last example of inner product in the space of continuous real value function. This is a class of function. For example, you have a polynomial function. You can have a sine function, cosine function, exponential function. Any function that is continuous on the finite support uh, interval A and B. All right, that set is a vector space. But now, if you can define an inner product, I can take f that belong to this set. I can take another function g belong to this set. And if I say a way to measure a relationship between these two guys, I'm going to use this notion. I'm going to integrate. I'm going to multiply two function. Okay, that becomes a new ft times gt. And what I'm going to do is that I'm going to integrate any area, the area under the product of f and g. You can also show the same way. I'm going to show the linearity first, alpha a plus h and g, right? So I'm going to check whether it satisfies the inner product property. So this is the alpha ft gt, sorry, ht times gt dt. I hope that it's clear to see that this is integral of ft gt plus the integral of ht gt dt. So this is the inner product between f and g plus the inner product between h and g. You have linearity in the first argument. We should see the last property. How about when you take the inner product of f with itself? The definition would be ft squared dt. So it means that you have a function f, and when you make the square, remember when you make the square, the magnitude would be non-negative, right? Because square thing. And whenever you take an area under the curve that return non-negative value, obviously the integral is only 0. Okay? And how about when this guy is 0? What happens when you integrate something non-negative but it returns 0? That's only occur when the function f is entirely 0 for all t, right? So it satisfies the positiveness, definiteness property, the last one. This is an example of typical inner product that you see on the Euclidean vector space on the set of matrices, rectangular matrices, and on the set of um, continuous functions on the finite support. I can also give an example of something uh, more concrete. For example, if I'm interested in the interval of 0 to 2 pi, okay, My ft is sine t, my gt is cosine t. Maybe the question is, what is the inner product between these two functions? What you do is just to apply the definition 0 to 2 pi sine t and cosine t dt. Just that. What is the integral of this? I hope it's not hard because you can change it to the sine of 2 times the angle, right? 0 to 2 pi. And that integral turns out to be 0. So inner product between sine and cosine t, right, with respect to this set is 0. Mhm. A vector space that has an inner product defined, that could be more than one inner product defined on a particular vector space. Whenever that happens, your vector space is called an inner product, because now your vector space has a nicer property because you can talk about a relationship in terms of inner product between two members in the vector space. Let's see some interpretation of inner product in real applications. First one is that suppose that your matrix X has n elements, all right? Suppose you have a rule in define members in X that your X or Y is occurrence of some events where it equals to 1, okay? Whenever it equals to 1, it means that it equals to 1 at the jth element. It means that the jth event occurs or something, all right? So whenever you define like this way, when you take an inner product between x and y, of course, x1, y1, dot, 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 xn, yn. So that's going to give you the total number of indices that the two vectors are both 1. So it represents co-occurrence of events of your interest. In machine learning, typically you have feature vector f. You could have feature f1, feature f2, dot, dot, feature fn. Okay, and you're going to put a weight on it. W transpose F would be W1 dot dot WN Fn. If you put W1 to be high, Wn to be low, it means that whenever you put inner product between WF transpose F inside the model, it means that you put more weight, you put more importance degree to the feature 1 as compared to the feature n. Okay. In the third example, suppose your vector f uh, is a value, so in probability, so you have outcome I from 1 to n, all right? Suppose fi is the value, is the some value with if the outcome I occur, and the vector p1 dot dot pn is a probability vector of the ith event. Okay. So of course, F transpose P is going to be F1 P1 and Fn Pn. What is it? This is the expected value of of the expected value. Remember, expected value is whatever that expected value of something is, that thing times the PMF, which is the probability vector P. You can also use inner product when you want to represent polynomial evaluation. Suppose your polynomial function of degree n is expressed this way. So you can write it as C0, Z1, dot, 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 Cn. You put the coefficient of that of each term into a single vector. And if you transpose it and with the value of 1 t dot 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 t to the n, right? That is exactly the polynomial evaluation at t. Okay. Hmm. Um, Probably we stop here for now. As you can see, example, I think we have a lot more example as we see the lecture along the way. But let me stop for now. We're gonna explain in the next video that now we have inner product. You can talk about the so-called orthogonality property of two vectors or two entities in the vector space. You can talk about how one thing is perpendicular to other thing. Okay, and this concept is very useful in a lot of applied problems. For example, projection problem. So we stop here for now.